done it last time, right?
Yeah. Just making sure everyone remembers. All right, so one of the things, so first we're going to talk about dual spaces. So dual spaces, of course, we have, some vector field V over a field F, usually, R or C. Other real numbers are complex numbers. And yeah, so we define the dual space of this is the collection, or V prime, just equal to all, it's equal to all linear functionals that map the vector space to the original field that are W is linear and continuous. So what these are, let's see, again, these are also vector spaces in a sense. Usually they have the same structure. I think that kind of breaks down when we go up to infinite dimensional vector spaces like we are here with functional analysis.
What do you mean by it breaks down?
They don't necessarily have the same structure.
What do you mean by the same structure?
Like the same elements in the field, I guess.
I don't
I'm
understand.
explaining. Yeah.
I think they completely, maybe I'm misleading, I missed something, but they're completely isomorphic. Can you give an example when it doesn't have the same structure?
Not off the top of my head.
Okay, go.
Yeah, examples where they have the same structure, like LP. But, yeah, so what we have then, now if we suppose that our V is a Banach space, then of course it also has some associated norm. Because of that, in order to have all the functionals in its dual be linear and continuous, then we have to have the condition that there, for some constant c, the I guess this holds for. Yeah. So for all vectors in V, then the functional applied to V is bounded. It's equal to some constant times the norm of V. And because of that, because this is still bounded, and we can also put a norm on that, and so that implies that if V is a Banach space, its dual is also a Banach space. Right. So an example of this.
So what's the norm?
The norm V.
In V prime, in the dual space? So you need to introduce the norm of a linear functional, right?
Yeah. So that's going to be, I believe it's...
So the norm of omega is what?
I think it is the norm of omega acting on V divided by the norm of V.
Well, but it would depend on V, right?
Yes. Is that, for all V less than...
No, not exactly. Well,
Is
this thing depends on V, but the norm of omega should not depend on V. It's the supremum of that,
Right.
over all V's.
Yes.
Or you say V equal to 1, then you don't need to divide it by it.
Okay. Thanks. All right. So yeah. So there's the norm on the dual space.
So you could prove that this is indeed the norm and satisfies all the axioms of norm.
All right. So for a specific example, we have the LP space, again the set of all functions such that all functions such. Let's do this right. So for f in there.
absolute value.
Oh, wait.
No,
No,
absolute
well,
value.
That's the
yeah.
value of f. Okay.
And you need to indicate a domain.
Yes, I'm trying.
What is it? Is it over R? Or just put omega,
Yeah.
LP of omega, and then this is omega.
Mhm.
It's in the notation of LP. Yeah, omega.
Okay, thanks. So if we have that, so given that space, kind of, it's the interesting fact is that if we have take its dual, here omega prime, and that is exactly equal to L of Q of omega, where 1 over p plus 1 over q equals 1.
Brackets.
Hmm?
Parentheses of omega.
Okay. And that comes
Well,
from,
in that sense, yeah, the Q is not equal to P in general, and that's different.
yeah, and that's, I think it's the Cauchy-Schwarz inequality when we have p and q equals 1/2.
So if P is 2, then Q is 2, and that's Hilbert space.
Mhm. And like I said, and that comes from Holder's inequality, which is with the same restrictions on P and Q, which is just a way of relating the norms of two different vector spaces.
So on the left is one norm?
Yes. So I believe that holds for little l p as well. This inequality. All right. So one thing we have there is from when V is a Banach space, its dual is a Banach space. So if we take the dual of V prime, then the dual of that must also be a Banach space. And what we can do with that is, because of that, it goes through and that then establishes a relation. They call it kappa. So we then have a map taking V to its second dual, and that is a linear map. So we have then that.
Well, isn't that isomorphism?
Yes, there are some.
Bijection.
Mhm. Is the relationship there? So I believe then you can set up
So
specific.
this is for any V, right?
Yeah, for any V that's a Banach space.
No, for any V, this
Oh, yes.
equality.
Thank you.
I know such maps are called isometry, so this happens. So K is an isometry, so and you don't really need to distinguish two spaces which are isometric.
Yeah.
They basically the same.
Mhm. And then of course, similarly, you can also kind of define spaces that are as dual to themselves, self-dual spaces. Actually, with that, we if we put so if we say L2 from this inequality, dual of L2 is L2, for example. And of course, the dual of that is L2, and so on and so forth. So I guess with that was just kind of some general stuff about dual spaces. So I guess more important especially for theory of PDs, I think, are really the bounded operators, or operators in general, I guess. So we have, if we define the space L v W to be all continuous linear operators, say T, where T maps V to W. Then we have, where V and W are Banach spaces. then we can say that a map T to W in that set is, yeah, so that is continuous if and only if there exists a C less than infinity such that TV is less than C. Yes. For all values in V. So it's called a bounded operator because when, obviously whenever
Basically, it's a operator is continuous if and only if it is bounded.
yes.
By the way, that C less than infinity, that's kind of, well, redundant. I mean, if you say there exists a C, then it is a C. I mean,
Yes.
C cannot be infinity.
That was the notation the book used, so just wrote it down directly from that.
So C is just a real number.
Or complex number, I think.
No, I mean, these are real numbers.
Right,
Norm is a real number.
Right. Okay. Yeah, so then of course, similar to what we did over there when we defined the, when we defined the norm on the dual space, we can then define the norm of a bounded operator to be the supremum of V over V or V given V. So that gives us, in a sense, the norm of a bounded linear operator is what that gives us.
I know the linear function omega is a particular case of that when W is just R or F.
There's a few relationships amongst them. One of them is, so if we have two operators in the same set, T1 and T2, then we have the triangle inequality of their norms.
Well, it just says that the norm is the norm. I mean,
Yeah,
if this wouldn't
basically.
happen, then it wouldn't be a norm.
And I believe if we have, see, I didn't write this one down, but I believe if we have two spaces, so like L mapping V to W and L mapping W to say X, with, I guess I'll just write it out, I guess. Hopefully I remember this right.